Hi, it's a beautiful summer sunny day in Pennsylvania. I'm here in my backyard. I'm getting yelled at by the birds a little bit because I'm by one of their feeders. We've been going through a dry period lately, and I've let the grass grow out a little bit. We're expecting a wet period later in the week, and I'll probably mow it right before that. But this video that I'm about to head into my office to record, I'll go through a PowerPoint on it, and you can follow along with the PowerPoint, and there's a couple things to fill in, is on precipitation, specifically on IDF curves: intensity, duration, and frequency. Those are the three things that we use to describe precipitation. And actually, we'll have a similar thing for streams as well. So I'll head back in and we'll go through that presentation, and you can fill out the stuff as we go. See you in there. I'm going to introduce how we describe rainfall with intensity, duration, and frequency. Some of these slides I got from my colleague, now retired colleague, Finley Edwards. And this PowerPoint is available if you want it. So precipitation, we have, one of the weird things we do is we use the term depth for rainfall in inches. Well, no, the weird thing we do is we use the term volume to describe depth. So what was that rainfall volume? It was 2 inches. Well, that's not a volume, that's a depth. But so you'll see those kind of used interchangeably, even though we do have to calculate the volume from the volume. So that's just on the terminology there. IDF is intensity. In the US, usually we use the units of inches per hour. We might use millimeters per hour. It's all the same principle. Duration can be in minutes or hours. We use both of those. And the frequency is usually done in years. So when we say that was a 50-year rainfall, that's the frequency of the rainfall. That's the return period, or about how often that size rainfall happens. So the factors affecting the runoff, which is what we're interested in, are the intensity. So if it rains really hard for a short period, that might have more runoff than if it rains the same amount spread over a long time. The duration, how long it's raining for. The watershed area, again, we've done some calculations on this. We just multiply the rainfall by the area, so that obviously more area contributing to a spot gives more runoff at that spot. And the watershed characteristics. If we pave it, it all runs off. If it's forest, little of it runs off. We have a couple methods we use to calculate the runoff. Now, at this point, just kick back and watch this. We'll go back into the details of this later. So this is not really where we're teaching the runoff methods. It's just introducing it so you can see what terms go into it. The rational method, the flow, this is the peak flow in units like cubic feet per second, is C times I times A, where I is the intensity in inches per hour at the time of concentration. Again, we'll define this all later. So for now, just kind of click through it. A is the area, and we actually, for this calculation, we put the area in acres, and C is a rational method coefficient. Well, it turns out, and when I have a live class, we go through this in more detail, that acres per hour is very close, converts very close to a cubic feet per second. So we have I times A in inches per hour times acres, and somehow we get cubic feet per second in there. That's because there's an unspoken or unlisted unit conversion in C, but really an inch acre per hour is about the same as the cubic foot per second. So C ends up being really the fraction that runs off. The other method we commonly use is the SCS or NRCS method, or sometimes it's called the curve number method because it uses a curve number. The Soil Conservation Service became the Natural Resources Conservation Service, and the method was formed when it was the SCS. So you'll hear it called either of those, SCS or NRCS method, or just the curve number method. And the calculation that goes in there is P is the We'll define these terms in a second here. Q is the storm runoff. It's not really a Q. We like to use Q for flow. This is not a flow. This is the runoff in inches. It's P. P is your design storm in inches, how much it rains. S is the storage, so how much that the site can hold, the ground can hold. So if it can hold an inch total of water, then the storage would be 1. The I is the initial. I don't see I in the equation. Oh, we could write this equation with an I in there, where I equals 0.2s. So I is the initial abstraction. So that's the amount it before it starts running off. So that's estimated about 20% of the storage is going to be taken up before any runoff starts. And like I've said about 5 times now, we'll go into this a lot later. And S can be estimated as, that's the storage, as 1,000 over the curve number minus 10. So for paved, the curve number is close to 100, so you get 1,000 over 100, which is 10. Minus 10 is 0. Oh yeah, so paved, the water doesn't really store anything. We actually use like a 98 for that. A common mistake that's made by students in tests and stuff is to take 1,000 minus 10 over the curve number, but it's 1,000 over the curve number, and then that minus 10. Q is the runoff volume, and again, Q is the runoff. We say volume, it's really a depth. It's not a flow. We multiply that by area to get the volume. And then there's a follow-up method, the NRCS NRCS peak method we can use from that to get a peak flow. And we'll do that later. So here is a figure showing, this is Pennsylvania. This is for the annual average precipitation in Pennsylvania. So I'm right now, where am I? One of these guys here in central Pennsylvania. And you see we annually get around 40 inches of rain per year. Now in 2018, we had a really big year. So we had 67 inches. 19 was 41, 20 was 38. We're pretty close to the average. So everything with hydrology, you have wide variations of things. So that's the average, but we can get a lot higher than that. And again, this is, where am I? I'm in Cumberland County right now. I just moved last year from York County to Cumberland County, just moved a few miles. So again, 2018, it was a very rainy year, and you can see a lot of this is blue and some parts are pink, meaning it was quite a bit more than the average rain that year. So that can vary a lot. This is in the stream that runs actually if you watch the intro video to the course, this stream I was standing by, you can see over a few years here the flow in the stream. This is the discharge in cubic feet per second. It's plotted on a log scale with time, and you can see that, because we had a lot of rain, we therefore had a lot of runoff and a lot higher flow in the streams. And we see we went over the flood stage several times in the stream. This is the gauge height, or the depth of the water, and you can see that follows the flow is calculated from the depth or the stage, and you can see the same thing here. So in 2018 into 2019, we went over flood stage several times. The rain can be measured in a couple different ways. I was project overseas for a few years. I measured the rain when it rained. I just had basically it was a tube with a funnel on top. So that's the easiest way to do it. You can also have it automated, where it collects the rain and then weighs it, and that's calibrated to calculate the rain, or just have a pressure transducer in there. or tipping bucket. That's kind of cool. So it fills to a certain volume and flips over, and then it counts the number of times it flips over. So here's a rainfall gauge, and this is one I took from Finley Edwards that he made. That's pretty cool. So that sits out there, and we've calibrated the opening area to the depth to calculate the volume of rain. This is the tipping bucket. So the water comes in there and it keeps tipping every time it gets full, so it knows how much it dumps. This is from one of the sites that we looked at when I was at the University of Arkansas doing research there. This is over a period here of several months, and you can plot the rainfall. So the purplish is how much it rained in inches for those days, and then I can plot the cumulative rainfall over time. So again, in the area I'm at now, which is pretty close to what it was in Northwest Arkansas, on the average, it's about 40 some inches a year. This is just over one storm or a few days, and we can see that we had a cumulative rainfall of over 6 inches for that storm. That was a big storm, by the way. So the frequency, the way we calculate the frequency, and I have this chart here that we're going to fill out, this table. When I do this for a live class, I actually print this out and then have them fill it in. I'm not going to do that here, but you can print it out if you want and fill it in with the notes. So the way we come up with the frequency, like again, what we're talking about there is the 10-year storm means a storm that happens about once every 10 years. 100-year storm is a storm that happens about once every 100 years. How do we come up with those numbers? Well, we get the annual rainfall data, how much it rained total for the year. For each year and each duration, okay, IDF. F is frequency, duration is D. So we come up with, for the rainfall data, what was the biggest 15-minute rainfall during that year? What was the biggest 1-hour rainfall for that year? What was the biggest 6-hour rainfall for the year, and so on. So we extract the largest storm of each duration. We rank them, largest to smallest, and we calculate then the return period is n. What is n plus 1 over m? Okay, so n is the total number plus 1 over m. So there's a couple different ways to do percentiles. For this we do, and this is the most common in other applications too, but there are different ways to do it. We have n plus 1, so that means nothing is ever the 100th percentile. So the percentile would be the rank over n plus 1. So we never quite get to the 100th because there could always be one bigger one out there. So the return period is actually the inverse of the percentile. That'll be, if you didn't understand all that, will be clear when we go through the example. N is the total number of events, M is the rank. So the probability is the inverse of that. So if we have 99 years of data, the one that's number 1 in that has a return period of n. 99 plus 1 is 100 over m is 1. It's the biggest one, is your return period of 100. So the percentile, or that's the probability that will happen in 1 year, is m, 1 over n. 99 plus 1, 100 is 1 over 100. So those are inverse of each other. So a 100-year storm has a 0.01, a 1% chance of happening in a year, and happens about once every 100 years. So here's an example. So just to take a simple example, let's take 6 years, and we have the largest rainfall of that year. I think this is the 24-hour rainfall. So I'll put this in this table here. So the first step we do is we'll rank these. So this is the year, and now I'm going to put 92 as number 1, 91 as number 2, and so on. So I'll rank those 1 through 6, and then the return period is n plus 1, so 6 plus 1 is 7 over m, and then the probability is 1 over that, the inverse of that. So the first one is, it was 6 years, n plus 1 is 7 then, over m of 1 is 7. So that's a 7-year return period based on, we just have 6 years of data. And then the inverse of that is 0.14, or 14.3% chance that you'll have that one that big or bigger during any year. If I go through that, I fill this out. The smallest one actually has a 1.2 year return period, and about 80%, based on these 6 years, we could have hit 6 real rainy years or 6 real dry years, but just based on our data, we would estimate that each year there'd be about 86% chance of having a storm of 0.25 or bigger. You say, well, wait a minute, 0.25 is a lot smaller than 1.65. Yeah, but that's all the data we have. So we have to go from that. As we get more data, we can modify that. This is a map of isohyatl. Iso means same. So isohyatl must be the rainfall then. Isohyatl maps. These can be obtained through a document called TP40. And you can see there that in the region I'm in, the 25-year frequency, 1 hour duration storm is about 2.2 inches. Whereas down in southern Florida, you get a lot more big storms. It's like 4.2 inches. Out west here, it's a lot smaller than that. So these can be represented in an IDF curve, intensity, duration, frequency. So rainfall intensity on the y-axis here, the duration on the x-axis, and then we have a different curve, different for each return period. So for example, if I look at the 5-year, what is the 5-year 60-minute rainfall? That means a 60-minute rainfall that's going to happen, one that big is going to happen about once every 5 years. I come up to, it's about 1.7 inches per hour. So for Chicago, a storm with a 5-year return period that lasts for 1 hour has an intensity of 1.7 inches per hour. Or the other way to look at it is in Chicago, which is Milwaukee's largest suburb, a storm with a rain at 1.7 inches per hour, come over here, that lasts for an hour is likely to happen about once every 5 years. And there's an IDF exercise I'll have you do after this, but I'll do a separate little video walking through that. What is the average intensity for a 24-hour storm with a 5-year return period? 24 hours, 5-year return period. We come over here, and it's about 0.12 inches per hour. So back here, 1.7 inches per hour. That's a big storm. It only happens once every 5 years, but that's not going to last. That's for 1 hour. It's not going to keep raining that hard for longer than that. Every 5 years, you have for 24 hours, it's going to be about 0.12 inches per hour intensity. What is the By the way, the total rainfall then, I would take that inches per hour times 24 hours, and I'd come up with the total rainfall for that day. What about a 100-year return period? So for average 5-minute storm with 100, once every about 100 years, it's going to rain about almost 10 inches per hour. Well, what if I don't have 100 years of data? Well, you extrapolate it out. So back what I said with that, the 0.25 was real low. I start with that and I can extrapolate out how much total rainfall occurred during the storm. 10 inches per hour times 5 minutes, converting units between hours and minutes, I get 0.83 inches total rainfall. So this shows for some different places. So this shows for Chicago, Seattle, Santa Fe, New Mexico, New Orleans. New Orleans, a lot of rain there. So you can see the intensities are higher than Santa Fe. Oh, wait a minute. Seattle, I thought Seattle was so rainy. Why are these kind of low down on there? Well, maybe it rains a lot, but you don't have super intense rain. So you might have rain more often. So this part here in Seattle is higher than this part here in Santa Fe. So for a day you might have more rain, but Santa Fe might have some real short, intense storms. So you can see the characteristics of this from these IDF curves. We can also represent this data in tables. So you can see the same thing here. You can pick out the 10-minute, 10-year storm would be 6.08 inches per hour. And then typically 5 minutes and 60 minutes are given 1-minute increments. And then after that, we go 2 hours. All right, so that's a little summary of the IDF curves. I'll do another video where we go through the example, the exercise. I do have in here a section in the PowerPoint on converting point precipitations to aerial precipitation. So if you're trying to get the rain over a whole area, what number do we use? How do we average those? I'm going to skip through this, but I'm leaving it in there just in case somebody wants it at some point. I can go back through it. All right, I'm going to go to summary slide here. Get there? Whoop. So important parts is that we can measure the precipitation, the depth of rainfall, which in some methods we call the volume, even though it's not a volume. And then we graph precipitation versus time, and we have different curves for those for the different frequencies. So we have the IDF curves. Usually is what we use, the intensity, duration, frequency. Okay.